Hello. In the last video of this semester, we are going to talk about ramps and elevators. So let's take a look at our subjects. First, we are going to remember what were the types of vertical circulation, and then we are going to talk about the function of ramps and properties of ramps and structure of ramps. We need to take a look at the safety issues, and then we move on to the elevators, like the properties parts of elevators and minimum required sizes, cabin types, again, the safety, and the last sub-subject is the structural stability. Let's remember basic options. Here, we had this slide before at the beginning of the stairs subject. You remember we either indicate the pitch with the angle or with a percentage. Here we see different angles, and the angles of the slope between 20 degree and 60 degree can be named as stairs. We can have stairs in various different pitches in between these angles. But if we need a slope that is lower than 20 degree, then we should either design a ramp or escalator. And if you need something larger, bigger than 60 degree, then it's called ladders. We can have rope ladders. It's a vertical surface now. And there's this line here. The other side of the line will be the elevator. It's the moving cabin. Let's start with the ramps. Why do we need ramps? Uh, these are inclined surfaces with the same purpose of these stairs to provide smooth transition between different levels to provide users to go from one level to the other level. But it doesn't necessarily have to be functional. Of course, we have very nice examples in addition to its functionality. Uh, this is especially important for wheeled equipment and people with walking difficulties. This can include people with wheelchairs or elderly people who needs to have a walking stick, or blind people, or people who needs to carry heavy stuff instead of using the stairs. They can be more comfortable with the ramp. They can be carrying heavy food, garbage. As you know, there are functional buildings specifically designed to have lots of food or garbage or sheets, clean sheets, towels. These are required to move from level to level, such as restaurants or hotels or hospitals even, or strollers, bicycles, luggages, or gurneys. These all have wheels, so ramps will be better. Like all the other elements that we have been talking throughout the semester, the design is not just related to functionality. It has also aesthetic properties. So we need to consider them, such as these nice examples. This is a very good example, in my opinion. I don't know the function of the building, but you can search for it and have different images yourself. It doesn't necessarily have to be inside the building, of course. We have this Contemporary Art Museum of Oscar Niemeyer, and the ramp, its main entrance, this red ramp is the main determinant of the building, and it has a very nice effect on the whole building. How can we make proper decisions about the ramps, functional decisions? We need to take a look at the properties of the ramp. we need to make decisions about its slope. The most important property, its slope. Either we can indicate it with this angle or percentage, using percentage. This width, just like the width of the flight of stairs, we have the width of the ramp. Uh, we need to make a decision if we need a landing or not. If so, we need to make the decisions about the sizes of the landing. Handrail or guardrail and/or guardrail may be required. And the form of the ramp, we can have different geometrical forms. We can make decisions according to the properties of the user, such as their age or number. If we are talking about a user that is a baby, a toddler, or an adult, and the number of people, again, directly related with the function of the building. Some buildings has public functions, such as educational buildings or healthy buildings. So also they will have uh, mm, a higher number of users. Also, again, based on the function of the building, the equipment they are going to use, such as the walking aids, things like that, stuff they carry. Uh, Properties of the wheeled vehicle, the wheelchair, stroller, luggage, gurney, bicycle, and the cars, the automobiles and other types of motorized vehicles. Uh, let's start with the slope. We can determine the slope based on the automobiles or wheelchairs. Let's first take a look at the automobiles. The maximum slope for an automobile to go safely should not exceed 15%. When we say 15%, it's I'm sure you remember, but let me remind you one more time. We do the percentage like this. First, we have a horizontal line that is for 100 units. This can be 100 millimeters, 100 centimeters, 100 meters. It doesn't matter. We have a perfectly straight horizontal line for 100 units. And then at the end of this line, we go upwards perpendicularly for, let's say, 15 units. If the horizontal line is 100 millimeters, then we need to go upwards for 15 millimeters, the same unit. If it's for 100 centimeters, then it needs to go upwards for 15 centimeters. And we need to connect the first point and the last point. So we have this inclined line. The slope of this line is 115%, because it goes 15 centimeters upwards for 100 centimeters. That's why we call it 15%. As you know, either with the angle or the percentage, uh, as the slope increases, it will be harder for using the wheelchair. Uh, this slope, the user can push themselves. They can control the wheels because it requires a strength and upper body strength. But if you increase the slope, then it will be very hard for him to push that the wheels, because it will get heavier. So an electrical device can be used for the slope. If the slope is increased, then someone else needs to push. But there is a limit for that because of the weight of the person. So for the wheelchair, maximum slope should be 6%. We should not exceed 6%. Again, we need to go for a straight line for 100 units, and then we need to go upwards for 6 units. When we connect the first and the last points, we will have a slope that is 6%. But there is a exception here. If it's a short ramp, the slope can be up to 8%. The maximum can be for 8% for a short ramp. Okay. We need to be careful about that. It doesn't matter. It's for motorized vehicles or wheelchairs or with any device that has wheels. You need to apply a certain amount of power. You need to push it, even if it's a stroller, if it's a luggage. And we should always remember that as the slope gets steeper, it will be harder for the user to push it. So those limits, 15% for cars and 6% for wheelchairs should not be exceeded. Uh, what type of forms can we have? We can have a straight run, just like the forms that we learned for the stairs last week. We can have a quarter turn, an L-shaped ramp. We can have a U-shaped or half turn ramp that allows the user to turn for 180 degrees, or we can have circular ramps. Uh, and this portion here is called the landing, as you know. It cannot be smaller. The sizes of the landing cannot be smaller than the width of the lamp. But for wheelchairs, it takes a larger area. It needs a larger area to rotate. So we need to consider that the minimum required size for a wheelchair to rotate around itself is 150 centimeters. So for the ramps, if you are designing the ramps for people who needs wheelchairs, we need to have at least 150 to 150 centimeter square area at the beginning of the ramp, and the length, the horizontal length of a ramp shouldn't exceed 10 meters. Because after 10 meters, it will be very difficult, very tiring for the person to push themselves or for someone else to push the wheelchair. What happens if we need a ramp longer than 10 meters? Then we need another ramp landing. We need to provide that person for catch their breath for a while. It doesn't matter if it's a U-shaped or an L-shaped ramp or a straight run ramp. After 10 meters, we need to provide a landing at least for 150 centimeters. That's the same for the U-shape, L-shape, or a straight run. Because 10 meters is the limit for their power. They need resting. How will the loads be transferred? We need to think about the structural components of the ramp, just like we learned the structural components of the stairs. Uh, there will be loads once the user steps on the ramp. The load of the user, the load of the wheelchair, the load of the stuff they are carrying. All these loads will be applied over the surface of the ramp. So it needs to carry the loads, uh, and it needs to stand on its own, and then we need to relate or integrate the ramps with the structural system of the building so it can transfer its loads to the structural system of the building. Just like the same rules can be applied that we learned for the stairs. Uh, the structure, it's very similar. We had main types of structural system for the stairs. Stair slabs, load transferring steps, cantilevered steps, steps with carriages, and stair slabs. Uh, we can do the same thing for the ramps. The only difference will be the upper surface is not profiled like the stairs. It's a smooth surface. So let's take a look at the first group. We can design a ramp out of concrete, reinforced concrete, or we can use a stone material. When we place the ramp like that, the loads will be directly transferred to the ground. So that's the example of load transferring ramps. Or we can have a cantilever ramp. just like the stairs, it will be connected to the structural system of the building, a load-bearing component, either a shear wall or a masonry wall. It can be a stone masonry or brick masonry, or we can have an inclined beam, something that can carry the loads of the ramps, but it needs to be connected on one side. The other side is unsupported, so that's why we call it cantilevered ramps. We can use carriages or inclined beams in order to create the ramp. And when we cover the upper surface of these inclined beams with a smooth panel, let's say, then we will have our ramp. And we can do these carriages as much as we need it according to the load and the dimensions of the ramp. And as they get elevated, of course, we need to have vertical components like small columns to transfer the loads uh, to a surface. Uh, and the last slab stairs, we can have a reinforced concrete ramp that can stand on its own, or it doesn't necessarily have to be reinforced concrete. We can have the same thing out of concrete as well, depending on the sizes and the connections. In this example, we have the form, the mold, and we have the reinforcement bars. So when they pour the concrete in and wait till it sets, and then they are going to remove the mold and the ramp will appear. It can stand on its own. Right now, it's supported with the scaffolding, but once it sets, once it's strong enough, as they take out the molds, they are going to take out the scaffolding as well, and it can stand on its own. The only important thing is it needs to be connected to the structural system of the building from the upper part and the lower part so that it can transfer its loads uh, safely. How can we provide safety and accessibility? When we say safety, the safety of the user, of course, we are talking about. If required, depending on the slope and the height of the ramp, we may need handrails and or guardrails. If there is a risk for user to fall down and hurt themselves, then we can design handrails and guardrails. And the surface material, it's important, especially for outside ramps. If the climate is rainy, snowy, a cold climate, there's a risk of slipping, so we need to provide a surface that prevents slipping and falling of the user. Here you see we have a textured material which is strong against the outside weather conditions, and there are strips uh, here, so they create a resistance. They create very tiny height differences so that the user or the wheels of the vehicle it resists to go back or fall back. Uh, Especially the entrances, you remember we talked about this grade level. It's good for the rainwater and it has some other good properties. But when we have that grade level, we need to either provide steps for the entrance of the building, but when we do the steps, we need to design a ramp so that people with wheelchairs, walking disabilities, older people, younger people, people who needs to carry stuff can use the ramp as an alternative. And that's very related to the slope of the area. Again, I'm sure you remember one of our previous videos, we talked about site grading. Depending on the slope of the area, we need to design the building integrated with the slope. That's not a good design to fill all the area, all the slope to have a horizontal surface and then construct the building because we need to create lots of retaining walls and it's dangerous. Or vice versa, we can just excavate the whole area, then the building will not have a leveled entrance. We need to create these very weird entrances or bridges or something. Uh, this is same for the accessibility. If we cannot control the slope as required, then it will be very hard for the user to climb up all the stairs for them to enter the building. And we need to think about how they are going to access the building without in problems. And first elevating the entrance, creating all these steps, and then creating a very funny, idiotic, unnecessary ramp next to it is not a proper solution. We need to make good, accurate decisions about the grade level and the ground floor and the entrance based on the slope. We can change the slope, but it needs to be logical, not excavating the whole area thoroughly or filling the whole area to have a level surface. Okay, uh, let's move on to the elevators. How does an elevator work? Uh, this is the view of the cabin of the elevator. It's kind of a small room that we step in, and it carries us up and down on a vertical direction. Uh, and it is a system. It's basically very simple. We have a platform here uh, that moves. So we need to step on the platform, or it can be a closed small room, which we call a cabin, or it's called a car as well, something like that. Then we enter the room and it either moves upwards or downwards. And there is a mechanism that allows us to go up and down in this moving platform or cabin. Uh, Two different systems. The first one is pulling the platform from above. The other one is pushing the platform or the cabin from below. Uh, what are the basic components? Let's take a look at both of them. The one that pulls. These are called electric elevators, but in my opinion, it doesn't make sense. In Turkish, again, it's called electric elevators. It doesn't make sense because both of them, the one that pulls from above or the other one, the one that pushes from below, they depend on electricity. They work on electricity. So it doesn't make sense to call them electric elevators. Instead, I think they can be called these type, the one that pulls from above can be called elevators with counterweights because that's how the system works. We have counterweights, and there is this mechanism with these gears and strings and cables that runs with electricity pulleys. These are called pulleys. Uh, and as the counterweights go down, the cabin raises, or vice versa. If we want to move the cabin downwards, then we need to raise the counterweight. So the mechanism is on the top and it controls the direction. Uh, Here is the anatomy of an elevator. Let's take a look of its components one by one. I know it looks complicated, but it's not. It's simple. Don't be intimidated with the all these different mechanical things. That's a section of the same thing. Uh, let's take a look at all of them, all these components one by one. First, we have the cabin here on the section. It can be called a car as well. It's the moving platform or closed small room, and it moves through a gap. That gap that goes from the lower level of the building to the upper level of the building, like a well. It's called a hoistway. It's called a hoistway, an empty vertical gap, so that that cabin can move freely. Uh, in Turkish, we call it asansör kuyusu. It's very similar with the stairwell. In Turkish, it was called merdiven kovası. Here we call it asansör kuyusu. Kuyu means well in Turkish. So it's the hoistway. It looks like this. And there are floors. These are the floors. And right now the cabin is at this floor. Let's say this is the ground floor, first floor, second, and the third one. Then the cabin is at the third floor right now, and people are waiting for the cabin to arrive, so they are going to step in the cabin to go down or up. Here we have the cabin. When the cabin stops at the floor, we can get off the elevator, we step on the floor, and there are doors here on the floor, doors on the floor. When there is no cabin here, like on the second floor or the first floor or the ground floor, these doors needs to be shut closed. Otherwise, there is a risk of users to fall in the hoistway. So they need to be shut down all the time, unless the cabin arrives. And when the cabin arrives, they need to be open so the users can pass through these doors to the floor or to the cabin. And these are called hoistway doors. From the floor side, when we look at the doors, when they are closed. That means the cabin is not at that floor at the moment. That's what we see. And from the hoistway, it looks like this. Generally, these are sliding doors, but it doesn't necessarily have to be sliding like that. Sliding doors, they doesn't require much area, but we can design other types of doors that can be opened in different directions in different ways. Uh, at the top, we have this area that is called a penthouse or hoisting machinery, makine dairesi in Turkish. It looks like that. There are lots of mechanical systems, these pulleys and gears and electrical devices, lots of cables, generators. Mainly, we have this motor generator set that controls the movement of the counterweights on the cabin. We have the traction machine, speed governor, brake, that's important to stop the cabin, pulleys, gears, and other mechanical stuff. All these parts are designed and implemented by a mechanical engineer. So that's not our job. We need to work with a mechanical engineer if we want to design a good elevator. Here, the cabin is related to that machinery with a traveling cable. And the other end of the cable, we have counterweights, karşı ağırlıklar. Uh, the traveling cable, it's mostly steel, it's very strong, and it holds the counterweights and the cabin and connects it through the penthouse. It looks like this. That's the upper side of the cabin. And this is the counterweights. These parts here are the counterweights. Uh, and that's what we see when we are at the bottom of the hoistway and looking upwards. This time we are looking at the bottom of the circular cabin, and we have these traveling cables, and these are the counterweights. Uh, we don't want our cabin to move sideways as it goes up and down. So we need a system to stop it moving sideways, swaying, and this system is called guide rails. It's generally on the either side of the cabin, and uh, it looks like that. These side parts. Uh, they are connected to the cabin, so the cabin moves in between them. These side rails, guide rails, they prevent the cabin to sway sideways. Uh, the bottom part is called an elevator pit, asansör çukuru in Turkish. It's just a lower, small pit, which has either strings or things that can slow down if there is a problem, if the cabin is falling, if there is a problem with the cable or the system and the cabin starts to fall. This pit and these strings, or we can call them buffers, they can slow down the crash. They will help with the crash. Uh, so we talked about the one that pulls from above. Let's take a look at the one that pushes from the below. Uh, Obviously, we don't need these cables, these machinery, the pulleys or counterweights anymore. Instead, we don't have that. Instead, we have something that we call a hydraulic system. That's a car or a platform is that's supported by a piston that is moved by a pressured fluid. And that piston can be in the central, below of the cabin, in the center part of the cabin, or at the sides of the cabin. So in this example, we have the pistons that move the cabin on the sides. And as you can see, the machinery is at the bottom this time. We don't need a penthouse at the top, and that's the section. But we still have the pit in order to have this buffer part for the accidents. And the rest is the same. We have the hoistway, the cabin, the guiding rails, everything. No penthouse is required at top. The machine room is on the ground floor or the basement floor in the lower floor. So these are the basic components of the elevators. How can we determine the required dimensions for the elevators? Let's take a look at the sizes. Uh, there are different firms, companies that produce elevators. One of them is Otis. That's an example. You can find many different national or international the elevator companies. Otis is one of the popular ones. So when you have time, take a look at their website because you are going to see different types that they produce, they design, and you can download their catalogs, brochures with all the required details. So we have the cabin. They produce the cabin. This can be a platform or a room like that. Let's imagine it's a room like this. So it has this small floor area, walls, and the ceiling, but made with light material, of course, not with very heavy materials like bricks or concrete or something. And there is this doorway of the cabin, so we can step in. As you can see, there are certain measurements, dimensions, like this width of the door or the height of the door. And if we have a plan of the cabin, that means that we are cutting horizontally this whole cabin. This is what we are going to be looking at. We have the cut surfaces as the walls of the cabin, and when we look down, we will see the floor surface of the cabin. Again, we have these dimensions, this width of the width of the cabin and the length of the cabin. So it has a certain area. That means we can have different sizes for the cabins, smaller cabins, bigger cabins. That depends on the function and the number of users and the weight, obviously. If we have a section, a vertical section this time, this is what we are going to be seeing. We are going to cut through the floor of the cabin here and the ceiling of the cabin, and that wall and the wall above the doorway and the gap for the door. Again, we have the door height, the cabin height, and that depends on the firm. There are different firms, and when you take a look their brochures, you will see they produce different types of elevators. So you need to pick a proper one for your requirements, for your needs, for the users. And this is just an example here. Let's take a look. B1. B1 is the width of the cabin. In this example, it's one of the smallest ones, just for an example. This width is 90 centimeters. D1, it's the length of the cabin, it's 100 centimeters. H4 is the height of the cabin, it's 2 meters, 17.5 centimeters. B2 is the doorway. It's 70 centimeters, and the height of the door, it's 2 meters. So, as I told you before, it's one of the smallest ones. When you take a look at different firms and different products, you will have different sizes. So first you need to make a research and pick a proper model based on your requirements, based on the sizes of the user, the number of the user, their the function, and everything. Let's imagine we have only one person, and the elevator will serve only for a person, and that person is a healthy person. He doesn't have or she doesn't have any walking disability. He's not going to move any stuff. He's not going to carry any furniture. He will be the only one that will use this elevator. So let's learn how we can decide about these sizes. That's the same person at the top view and the side view. So we have this width, and normally we take 60 centimeters for this width, but we don't want their hands or elbows to brush against the surface of the doorway or the walls. So we can have 5 more additional length. So instead of 60 centimeters, including 5 and 5 on either side, we can have 7 centimeters. That's why it's the minimum. 7 centimeters is the minimum. It's only for a person to pass through without hurting their shoulders or elbows or hands. And the height, again, we can take a standard person that can change on the race or the country. Like the people in the USA, they are much taller and bigger than people in the East. So again, it can change, the standard can change, but for Turkey, we can have a standard height for 1 meter 70 centimeters, 1 meter 80 centimeters, or 90 centimeters, maybe. So we can determine this height according to the person. But if the person is going to be carrying stuff, these can be boxes, or it can be a furniture. like a sofa or a refrigerator, then this width for the door for 7 centimeters, it won't be enough. It needs to be at least 90 centimeters, 60 plus 15 on each side. So the total will give us the 90 centimeters. 90 is the minimum. We can have bigger doorways based on the furniture or the equipment that we are going to carry. Again, for a refrigerator, a big refrigerator like that, uh, 2 meters will probably will not be enough. So based on the function of the building, based on the analyzes about the user, their activities, their sizes, their biological properties, we need to make a proper decision about the sizes of the cabin, and we need to pick one model from a company, or we can ask them to produce a special cabin for our requirements. And the person can be using a wheelchair. Again, the sizes will change now because now he's sitting, and there is this width of the wheelchair, and if he's using it with his hands, then there will be his hands pushing the wheels on the sides. So 90 centimeters is not enough. We need to increase that width be to the width of the doorway accordingly. It needs to be at least 1 meter and 10 centimeters for this type of wheelchair or bigger. And the sizes of the cabin, like this B1 and D1, they can be determined based on the number of people who is going to use the elevators, and that's directly related with the function of the building. If it's an apartment building with lots of flats, then there can be many users that needs to use the elevator at the same time in the morning period and in the evening period. Or if it's an office building or an hospital building, again, there may be lots of different users that needs to use the elevator at the same time. So the sizes of the cabin, the area should be determined based on the number of people. Uh, this is the typical appearance of different floors. We have this hoistway, we have this gap, and the gap needs to be bigger than the sizes of the cabin. It cannot be the same, otherwise the cabin will stuck at that hole. So we need to first determine the minimum required sizes of the cabin, that B1 and D1. And then we need to have a bigger gap according to the type of the elevator. If it's the counterweight, then this gap will also serve for the cabin, serve for that cable and the side rails and the counterweights and everything. So we have new measurements. We have this gap B3 and D3, and there is this machine room at the top in this type of the elevators, and it requires a certain size, a certain area, depending on these machines, B4, D4. Let's have a plan this time. For the plan, I cut through the cabin, and when I look down, I see the edges of the gap here and the edges of this floor area. So we have this B3 and D3, D2 for the sizes of the gap. And the section I cut through the floors. Here is let's say it's the ground floor and there's no basement. So we need to have this pit elevator. It's D3. That's the normal floor height. And once we have the floor height, we need this slightly elevated part for the machine. And this machine room, again, it needs to have a certain height, and there needs to be a lid here, so that if there's a problem with the machines, we need to have a worker, an engineer, or someone who understands how that machine works, how can it be repaired. So we let them through this hole, through this gap, up in the penthouse, so they can be there comfortably and repair it. So we need these measurements. Again, these are provided to us by the company. We need to take a look at their brochures, and that depends. These sizes depends on the cabin that we choose. So first we need to choose the cabin, and based on the sizes of the cabin, we need to take their brochures, take a look at their brochures, and find out what is this B3. For this previous example, the minimum B3 needs to be 1940 millimeters, D2 1750 millimeters. That's for the smallest one, the previous example of the cabin. And we have this D3, the height of the elevator pit is this. And you can see the other required sizes, minimum sizes. But again, I'm repeating, that's just an example. An example for the minimum cabins, one of the minimum cabins. First, you need to pick a firm and then take a look at their different options, different models, and decide a cabin based on your users' properties, user requirements, and based on the decision about the cabin, then you need to learn this hoistway sizes and the pit depth, and if there is this penthouse machine room at the top, then you need to learn its sizes, both horizontal and vertical required sizes. Once you get all this information, you can draw your plans and sections correctly. Otherwise, you won't be able to do the drawing. So these are the sizes. Let's take a look at the types of the cabins. Uh, the properties of cabins and elevators depend on the usage, number of users, the weight, that's related with the number of users, and again, that's related with the function of the elevator or the building, if they are going to be carrying heavy stuff, like in the factories or in hospitals or things. The number of users and the things that will be carried with the elevator will determine the sizes, and they are all depend on the function of the building, like an office building, a hospital building, a factory building. Like this example, it can be a school building or an office building. That's obviously a factory, and you can easily compare the sizes of the elevator cabin. It's much bigger because they are going to carry big stuff and heavy stuff probably, and that's called a goods lift or a service elevator. In some buildings, in some residential buildings, you can have two types of elevators. The first one is for people, only for the use of people, and there are warning labels for the maximum number of people or maximum weight that can be carried with that elevator. And if it's not allowed to carry furniture, heavy stuff, then they probably provide a second type of elevator, this goods elevator, and that's only for moving in and moving out. Or if they didn't design an elevator like that, then the people who is moving in and out can carry their furniture through stairs. They cannot use that elevator because if they exceed the limit of weight, then it will disturb the mechanism of the elevator, and it can be very dangerous. And for the hospitals, again, the sizes and the other properties needs to be related with the gurneys. And as you can see here, gurney is a bed that can move on wheels, and there is this ivy pole. There can be some other stuff in the sides. So first we need to learn the minimum sizes of a gurney, and then we can make decisions about the cabin, the doorway of the cabin, and based on the decisions of the cabin, we can make decisions or uh, learn or try to find out the required sizes for the hoistway and the elevator pit and the penthouse. We learned that in every floor there is hoistway door which needs to be closed when the cabin is in on at the different floor because we need to protect the user. If the door is open and the user is careless, they can fall in to the hoistway. But there's another set of doors on the cabin this time. Here on the plan, when we cut horizontally, we can show them like that. Generally, again, they're sliding doors. They don't necessarily have to be a sliding door. We can have different types of openings, but that's the minimum size. The type that requires the minimum size, and that's the section. Again, we cut through the doors. On the plan and the section, we need to draw the doors always closed, not open, the closed doors, and we can have small arrows to indicate where they are sliding, in which direction they are sliding. So that's a normal plan and a section here. But if we want, we can create the cabin and the doors with transparent materials like glass or other types of transparent materials. This time, the plan will change that line in the middle, a thick single line will symbolize the transparent surface, and these transparent panels cannot be able to stand on their own, so we need a frame. So these corner parts will the cut surface of the frame, and if we want, we can have not only one door or two or more doors in the cabin. In one floor, that door will be opened, so you can step in the cabin. At that time, this door is closed, and when you are on another floor, then this is closed, and that door will be opened, so you can step out from that direction. That's also possible, and that's the section of that transparent cabin. Again, you need to cut through this ceiling part and the floor part, and you need to cut through that transparent door. Again, this middle thick line symbolizes the transparent surface. There is this frame parts, and there is this upper transparent window part, uh, and that's the elevation here. Besides the elevators that carries humans and uh, goods, we can have smaller cabins, very small cabins, specifically designed for restaurants that can carry not the people, but the food, either food supplies or cooked food or dirty dishes. It doesn't matter. And these are called dumbwaiter in English, montage in Turkish. Again, it's a French word. We took it from French. And as you can see, the principle is the same. The only difference is we have a much more smaller cabin with shelves according to the sizes of the food. And we don't step in the cabin ourselves. So there are two people in different floors. Let's imagine this is a restaurant with many different floors, and the kitchen is in the basement floor. So the dumbwaiter, when the dumbwaiter is on the basement floor, the cooks will load the dishes, the food to the dumbwaiter, and they're going to press a button, and it will raise upwards, and when it's on the restaurant floor, there is this waiter that takes out the food, and then the waiter can put the dirty dishes back inside the dumbwaiter and push the button and send it down to the kitchen where the dirty dishes will be washed. Uh, or instead of a cabin, we can have a platform without the walls or the ceiling, only a moving platform. Here is the design of Remcola's Maison Bordeaux. If you have time, please search for this building. It's a house building, and the design is very interesting. You need to learn about the story of the design, how the architect has designed it. And there is this moving platform right in the middle of the uh, building, and as you can see, there is furniture on the moving platform. There is a desk because there is this bookstore for 3 floors that goes through the height of the 3 floors, and it's controlled with a remote control. Here, it's a hydraulic platform. So instead of walls, we can have only a handrail and guardrail so that the user won't fall down. If so, that's what we need to draw for the plan. This time, when we cut horizontally and look down, we see the upper top view of this handrail, and that's it. And that's the section. Obviously, when we cut vertically, we cut through the floor and this handrail. And when we look towards one direction, we see the front view of the uh, handrail. That's it. Uh, it cannot. It can be at the size of the belly, which needs to be minimum 90 centimeters. But instead, we can have a transparent, not a glass, but made out of these, let's say, lattices all around the like a cabin, but it's not closed in the upper part. We can do that too, and it's called a bird cage elevator. It's mainly seen in old buildings, many old buildings. Uh, like the ramps, it's not just about functionality or technical requirements, but also the aesthetical properties, like this design of Foster Partners. The elevator is the facade of the building, and it's very interesting. It has a very effective uh, very good effect on us. Based on these technical issues, we need to provide the safety. And when we say safety, we are talking about the safety of the user, because when the cabin is not on that floor, we need the gap, and there is this risk of users falling down inside the hoistway. So we need to come up with a solution. Again, we can have a handrail and the guardrail, and a small door, of course. So when the cabin is not at that floor, that handrail and guardrail will protect the users from falling down inside the hoistway, something like that. The height of the handrail and guardrail can be arranged. It needs to be minimum 90 centimeters, but it can be higher, and it has its own door. As you can see right now, there is this cabin, but when the cabin is there, and when we do the plan, we cut through the cabin, we cut through the doors of the cabin. So we need to draw these with thick lines, and these guiding rails next to the cabin. And then when we look down, we see the top view of this handrail and its doors, and the rest is the gap. We'll see the bottom of the elevator pit, like that. And this is the section we cut through the floors here. That there's this gap of the floor, and we cut through the cabin with the doors, and we cut through the handrail and the guardrail, and the rest is the emptiness. It's nothing. Uh, So it's the plan and section of this design. It looks like this when there is no cabin. We are guarded by this handrail and guardrail. They are high this time, not only 90 centimeters, but higher than that. And you see the door, the hoistway door, so it's closed. Otherwise, there's this risk of users falling down. We can do that. Or we can design walls made out of bricks, walls made out of AAC or any other material. And around the hoistway, around this gap, we can design the walls. We can protect the user from falling down with these walls, and these walls can be up to the ceiling or they can be lower, it doesn't matter. And as you can see, when we do the plan, according to the height of the walls, we cut through the walls and we cut through these doors, the hoistway doors. These are the doors on the floor, and we cut through the cabin with the guide rails next to them and two set of doors. This time, these are the doors of the cabin. So when the cabin stops at the floor, two sets of doors will be open. The doors on the hoistway on the floor, and simultaneously the doors on the cabin will be opened so that we can step outside or step in. And when we look down, we can see the top view of this counterweights, and that's enough. That's what we need to draw for a plan. The same thing, the same principle will be applied for the section, vertical section. We cut through the floor, and then there is this gap, hoistway gap, and the floor can go like that. There is the other floor. We cut through the cabin and its door, and there is this hoistway door on the floor and the wall, the upper part of the wall, and there is this wall at the back, and the counterweights, and we see the cables and everything. This is the section that we need to draw. And the wall can be made out of a light material. It doesn't necessarily have to be heavy like concrete. We can use lighter materials for the walls. We can use bricks. We can use AAC. We can use gypsum boards. The only function of that wall is to prevent users to fall down to hoistway. That's it. We don't need anything else. And there needs to be a gap. Obviously, this hoistway gap needs to be bigger than the cabin, the sizes of the cabin. Otherwise, the cabin will stuck and it cannot be able to move. It needs to be bigger. But here, where it meets with the floor, where the user will step in and out, the gap needs to be minimum. There needs to be a minimum gap, a very slight gap. If the gap is bigger, then it's dangerous for the user, obviously. And for the hoistway door, for the door that is on the floor, we can design different types of doors. It doesn't necessarily have to be these metallic aluminum surfaces that slide sideways. We can have different materials and different types of openings for the door. Or instead of brick material or AAC material, we can use glass walls, walls that are transparent, walls that allow us to see the hoistway itself, like that, something like that. So it's all glass walls, and we can see the cabin. There are two levels or more. Right now you see two levels. So this level, there's this door on the glass walls. So it's closed now because the cabin is in the upper level. Otherwise, we can fall down. It's closed. And when the cabin moves at this level, this door will be opened and the doors of the cabin will be opened. We can see the doors through the glass surface. We step uh, from this direction to the cabin, and once we are on the upper floor, these doors are closed, but there are probably other set of doors in the opposite direction. They will be opened so that we can move on towards this direction. Okay, last topic. How can we integrate the elevator to the structure of the building? Again, we need to find the proper solution, just like we did this for the stairs and the ramps. Elevator, it has its own weight and it has our weight. So first, when we step on the cabin or the platform, our weight will be applied to the surface of the cabin. It needs to hold, it needs to meet and carry our loads, but it needs to transfer all these loads somewhere. Uh, Most probably it needs to be connected to the structural system of the building, but not necessarily, because we can create a steel structure or a timber structure, a separate structure for the elevator. This is some images from the video that is called "What's Inside Big Ben." I advise you to watch that video and follow that channel. There are different videos that explains how all these systems work. And as you can see, there is this steel structural system, very simple steel posts and column, the beams that connects all these posts. And inside this system, there is this cabin and the cables and the counterweights and all the other parts. So that's the system that carries all the loads of the elevator and us, the users. Uh, the only thing is that we can design that system out of steel or timber material. That's the same with the designing the building structure. We are going to place vertical columns or studs, and we need to connect them with horizontal beams so that the loads of the elevator will be transferred to that structural system. And then we need to connect these vertical and horizontal components of the elevator structure to the structural system of the building, to the main structural system of the building. We can connect the beams to the beams of the building. The columns can be applied over a raft foundation so that all the loads will be transferred to that raft foundation. We can come up with proper solutions. Here, we can see the floor, and when the cabin is at that floor, the doors will be open and we will step outside. So the elevator with its own structure can stand on its own. It doesn't need anything else. We don't need to create reinforced concrete columns or shear walls or anything else for the elevator to carry the loads of the elevator. We can design a very simple structure, steel or timber structure, and we can connect it with the main structural components of the building, and that's it. That's the thing that will carry the elevator. But normally in the market, when you are working on in an office, this is what you will see mostly. This is a typical apartment building. When we take a look at the project is not important, which project it is. You see many types of these structural systems, the elevator and the stairs. We see rooms. There is this elevator and the staircase, a very nice staircase. So we have a hallway. So there are probably two flats. When you enter from here, there's the entrance hall, the kitchen, the dining room part, or the living room. Here, there's this bathroom and main bedroom. And this is the other flat. When you enter, there is a smaller entrance hall, this bathroom here, one bedroom, the kitchen, and a living room. So a simple building with two flats, only one floor. Let's take a look at its structural system. As you can see, there are columns. placed by the architects, designed by the structural engineers. Uh, let's imagine if these were the columns. We learned that we can position them, some of them like this and some of them like that, so that it will be stronger against the lateral earthquake loads. Let's imagine the structural system is like this, and it's balanced, right? There's no structural imbalance throughout the building. So we have these grid lines and nice columns, and each column is connected to each other with beams. There's no problem right now. And during the earthquake, a balanced building, a balanced nice structural system will move, sway normally. That's normal for a building to move during the earthquake with the forces of the lateral forces. It will sway. That's normal. Uh, that's what we are looking for. But if there is an imbalance, such as instead of placing a column, if we have shear walls around the elevator in order to carry the elevator, or if we have shear walls around the staircase in order to carry the staircase, we create an unnecessary imbalance in the whole structural system of the building. First of all, we don't need shear walls to carry the loads of the elevator. We can design a very lightweight steel frame structural system for the elevator. The only thing we need to do is to connect it with these columns and beams, and that'll be all. Same with the stairs. Let's imagine we did this unnecessary, most popular uh, shear walls around the elevator. What happens during the earthquake? Earthquake is a lateral force. It will push the building to move sideways, but there is an imbalance weight-wise. We know that shear walls and columns made out of reinforced concrete material, these are very heavy objects. So when we change the structural system from this single column, small column, to a very large, big shear wall around the elevator, we create a very we increase the weight at this portion of the building, and the rest of the building will be lighter based on if you compare their weights. And during this lateral movement, since this part becomes heavier, it doesn't want to move, or it moves slowly because it's heavy. However, the rest of the building, since it's lighter, it needs to sway bigger. It needs to make a bigger sway. And we know that all these columns, they are connected with beams that carry the floors. And just can you imagine what happens? This portion, it doesn't want to move, but the rest of the building wants to move freely. So it will start to rotate. Uh, around this heavy part, and that will cause deformation in these connections with the connections of the beams. And once the beams are deformed, once they break, the floor starts to collapse down, and the whole building can collapse down. So that's very dangerous. That's very unnecessary. You can have shear walls not to carry the loads of the stairs or the elevator, but in order to do the stairs and the elevator, you create gaps in the floor. And just take a look at the last week's video, and during the class we did this on the board as well. When we create those gaps on the floor surface, we disturb the load distribution. So shear walls can help us to uh, make up for the gaps and for the distribution, that disturbed distribution of the loads. But when we do the shear walls, if you create a heavier part for this building and cause an imbalance, we can solve that problem by creating larger columns or even shear walls in other corners so that we can have a distributed, equally distributed load throughout the building so that again, with the lateral force, the building will sway normally without this rotation. We did this example at the beginning of the semester. You remember, I'm sure. Let's take a look right now. This is the geometrical center, central point. It's geometrical center. And what about the gravitational center, the weight of the building? Because all the columns are equal and because there is no imbalance with the weight throughout the building, the gravitational central point is at the same point with the geometrical central point. That's what we are looking for. If this is like that, if two central points meet, then during the earthquake, the building will sway normally, and when the earthquake stops, it will stop. No problem, no structural damage. But let's imagine instead of a normal column, we create this shear wall. It means because of the size and the material, this corner of the building become heavier than the rest of the building. And that means we still have the same central geometrical point, but the gravitational point, the weight distribution has been moved. Now it's here. It's closer to the heavy part of the building. They don't adjust. And during the earthquake, with the lateral force, the lighter part will want to move freely, but the heavier part needs to move slowly. It doesn't want to move, and it will break the beams, and it will end in the whole collapse of the building. So we need to find a solution. We can have bigger columns so that there is an equal weight distribution throughout the building. We can move the gravitational center back. There is one of the solutions. Or let's imagine we design a building like that. A portion has two floors, even maybe a basement floor, three floors, and this part it has only one floor, ground floor. Again, there is a load imbalance since we have three floors, basement, ground, and first floor in this side, and only one floor in that side. There is this load imbalance. This part is heavier. It doesn't want to move. It moves slowly during the earthquake, and this part is lighter. It wants to sway more. If we design the structural system like this, if you have columns and beams like that, and the columns for the beams for the upper floor, and also the gap for the stairs, obviously, if you have a structural system like that, since this part is heavier, during the earthquake, during the lateral force, that part will not want to move. That's the center, geometrical center. But since this part has three floors, the gravitational center has been moved towards the heavier side, and it doesn't want to move. So here, these beams, these connections will crack, will break down, and it can cause the part of the building, that part of the building, or maybe the whole structure to collapse down. Once they are broken, they cannot stay in their place, they will fall down. Here's a video that I wanted to show you in one of my previous videos, but the video didn't work. Now I arranged it. It's a camera view, security camera view from the one earthquake in 2011. It's a hospital. Let's take a look. During these lateral movements, the sway of the building, Here, that's very interesting. Okay, this is what I want to do. That's very interesting. Here, we are at this corner here. There are two parts that are separated in between. As you can see, this lighter part sways more, and this part, this heavier part, it doesn't want to sway, and we have a seismic gap there. A seismic gap. With the help of the seismic gap, there's this piece that uh, closes the gap. You can see how the difference between the sway, because it's elevated so much. That's good because with the seismic gap, that's what we call dilatation in Turkish. The building, it doesn't hold down, or it doesn't, the structure will hold. So that we can do the same. That's the other solution. Instead of creating the other part heavier so that we have a balanced structural system, we can separate the building. We can have a seismic gap, uh, and we can separate the heavier part from the lighter part. That means constructing two buildings side by side, but they are neighbors and they are not connected. There is a gap, a thoroughly gap from the basement, that starts from the basement and goes up to the roof, and there is no connection at all. Uh, a total gap without any connection between two buildings. Here is an example. The behavior of buildings that are symmetrical is complex, usually involving combinations of torsion and flexion. By using seismic gaps to separate the building masses, that's the design of the geometrical shape of the building. This part is heavier and this part is lighter. Again, the same problem. When the earthquake happens, it can break down. So in order to solve that problem, we create two separate neighbor buildings, but there is a gap only for 5 centimeters, but the total gap, there shouldn't be any connections. We completely separate the buildings, including the foundations, the roof, the floors, the doors, and everything, the walls, two separate neighbor buildings. First, we construct this one, all the construction is finished, and then we leave only a 5 centimeter or 3 centimeter or 7 centimeter or 10 centimeter. It can be calculated by a structural engineer, a gap. That's a complete gap. There is no connection at all. Nothing is connected. And we construct that other building, a neighbor building. Uh, but with that closing parts, these covering pieces, the users cannot be able to understand that they are in two separate buildings. They think that they are in one building because of the size of the small gap. So instead of designing the structure like that, first we do the seismic gap, dilatation in Turkish. First we construct this part. We have 4 columns connected with 4 beams, and we do the upper floor and the lower floor. Once the construction is finished, we leave the gap for 5 centimeters, a total gap without any connections, and after that 5 centimeter gap, we start to construct a new building. That means we need a 4 new set of columns now, and we have 4 new set of beams. They are not connected like this, so the plan has been changed. Uh, Previously, it was the grid lines are like this: 1, 2. It's still 1, 2, A, B, and C. As you can see, these beams are connected to the columns B. So without the seismic gap, during the earthquake, during the lateral forces, because of the instability of the load distribution, these columns and beam connections will be broken, and the structure will fall down. But with this seismic gap, now we have two separate buildings. A first building with four columns with four beams, and a neighbor building with four columns and four beams, and there's this gap, a total gap, no connection. The the foundations are separated, the floors are separated, the structure is separated, the walls are separated. There's a complete gap throughout the building. So we can change the name of the grid lines. This can be B and this can be B prime, something like this, or C, it doesn't matter. Uh, and how we can do the construction? First, we do, if it's a reinforced concrete structure, first we do the structure of these columns and beams. Once they are set, once the molds are removed, in order to create the new building, the neighbor building, these columns, we can use XPS boards. First, we can cover the surfaces of these columns and beams with 5 centimeter thick XPS boards. And then we do the molds for these columns. And those boards will work as the molds, and they will create that 5 centimeter gap, and they will fill the gap. So we don't need to remove them. We can leave them as they are. So the plan will change. Once we cut through here, we cut through these columns, and in between, we cut through these XPS boards, and normally we use that for heat insulation. So that's the hatch that we use to uh, show the cut surface of the heat insulation. So that's how we can do that construction. If we don't do that during the earthquake, these buildings can be separated even if they are not collapsing down. There can be a crack like that. That's why in Japan they use these seismic gaps, and they use wider gaps. In one of my previous videos, I shared a video that compares the adjacent building construction type with these seismic gaps in Japan and the ones in Turkey. The left side is from our country, the right side is from that video, that from Japan. And uh, we need to do the gap, and we need to create two separate buildings. We need to do two separate walls. That's an example from one of the earthquakes. As you can see, this building stands. There's no structural damage, but the next door building, the adjacent building, has been either demolished or collapsed down. And as you can see, the building that has been collapsed, it doesn't even has its own walls. It was using the walls of the neighbor. That will cause many other problems, not just structural problems, earthquake problems, but the noise problems. So we need to leave the gap. We need to use that XPS boards or some other, we can use glass foam or glass wool, glass foam, or some other material in between. And we need to construct two different walls if necessary, so that it will help with the seismic resistance and the noise insulation. That's the last example that I want to show you. That's from Izmir earthquake. It was something like 2016, 2018 or something. There are two adjacent buildings, two separate buildings, and they did this seismic gap. This building is intact, but this other has structural damage. It's not collapsed down yet, but it slightly moved. And inclined like this. If there was no seismic gap, this structural damage will probably cause this other building to be damaged as well. But with a correct structural gap, only that building is damaged and the other is been intact. There is no problem with it. Uh, as you can see, it moved sideways, and there are machines, big machines, that support it from falling down, prevent it from falling down. So that's it. That's all the things that I wanted to share with you about the elevators and the ramps. In this video, I'm hoping that throughout the semester we did the structure first, and then we did the floors, and we moved on to foundations and stairs, ramps, and elevators. These are the subjects of the Building Science 1. I hope all these videos will be very useful for you. I try to give you a basic knowledge and principles so that you can use that knowledge and principles with the examples during your design courses. You need to first learn all the knowledge and principles by heart. You need to understand their logic so that you can transfer all this knowledge into your design process. You need to come up with your own solutions based on these principles. You need to use these knowledge and principles during creating your own design solutions, design versions. I'm hoping that all these videos will be very useful for you. And hopefully in the second semester, there will be Building Science 2, and we are going to do the rest of the building elements. That's the roof and the walls. Uh, you can think them as the envelope of the building or envelope of the space. We are going to learn how we can design roof, what kind of principles that we need to keep in mind, what are the different types, and how we can design walls, including the doors and windows, the openings for the doors, like that. Hope to see you in next semester. Take care. Have a nice holiday.